Well, howdy, folks. Well, today we're going to walk you through a lab experience on oxidation reduction reactions. This was supposed to be a titration, but I'm just going to kind of walk you through the calculations and the mechanics of what we would have done had we been in the lab. But this idea of oxidation reduction reactions involves the transfer of electrons from one species in the reaction to another. The one that loses the electrons is the one that's getting oxidized. The one that gains them is the one that's getting reduced. And this kind of sets the stage for our upcoming discussions of electrochemistry in Chapter 20. So first, let's do a couple definitions. Oxidation, for instance, is technically the loss of electrons. Now, you'd think oxygen would have to be involved, and oxygen, don't get me wrong, is a great oxidizing agent. It will steal electrons from other things, oxidizing them, but the act of oxidation is the actual loss of the electrons. So for instance, when a metal loses its electrons, like iron, in its metallic state is iron 0, it's got 0 charge. But if we steal some electrons from it and make it into iron plus 2, it suddenly becomes more water soluble, in that ions are attracted to the polarity of the water molecules that might strike them, and consequently, if you were to pour, let's say, some acid on the fender of my truck, it looks like that's happened in the past, but essentially the acid is going to steal electrons from the iron that's in that fender, and sure enough, it'll change it into a soluble iron salt that will wash away. Well, it oxidized the iron in that case. Now, oxygen's pretty good at doing that, don't get me wrong. It just takes a little bit longer for the oxygen to eat through the paint and get at the iron in there to steal its electrons. But in that oxidation process, the loss of electrons by the iron is defined as oxidation. Reduction, on the other hand, is the gain of electrons. Now, that's always been a point of confusion for people, because you think reduction, the word reduce, means that you would lose something, but it means a reduction in charge. Remember that the electrons that it's gaining are negative in their charge, so something that gains electrons, its charge becomes more negative. For instance, the oxygen that steals the electrons from the fender of my truck, it becomes an oxide ion with a -2 charge on it. So as the iron got oxidized, the oxygen got reduced. These two things always have to occur simultaneously. Now, in order to understand how to look at this exchange in electrons, we have to look at, well, how do we assign charges to everything? Now, most of this we discussed way back in Chapter 2. We know, for instance, the group 1 elements, they always go +1 when they're in a compound. And the group 2 elements, they always go +2. We've kind of been familiarizing ourselves with those cations and simple anions since the very beginning. But sometimes the transition metals can put a little spin on this, because they have variable oxidation states where they have different positive charges that you'll find them at. For instance, we saw that iron could be iron +2 or iron +3, or copper +1 and copper +2. So there's a lot of transition metals that we had to assign a Roman numeral with in order to convey to anyone who looked at our formula written out that they knew which positive charge of that particular ion we wanted. Well, let's look at this a little bit more closely, assigning oxidation numbers to all the elements in a compound. All right, the first rules in assigning oxidation numbers, very simple. Something we learned way back, like I said, in Chapter 2. In a compound, when they're not just sitting at home alone with all their electrons, but when they've already entered into a compound, we know that the group 1 elements, like lithium and sodium and potassium and rubidium, they always go +1 in a compound. All right, now if they're sitting alone not in a compound, for instance, just lithium as a solid, that's got a charge of 0. It hasn't lost or gained any electrons. But generally, once it enters into a bargain and it's in a compound, lithium will always have lost 1 electron so that it could look like a noble gas. So they always go +1. The group 2 elements always go +2 whenever they're in a compound. But again, if they're in their pure covalent state, for instance, like calcium is in group 2, just calcium metal as a solid with no charge on it has an oxidation number of 0. But once it's in a compound, it always gives up 2 electrons to look like a noble gas. These two columns, without fail, always go +1 and +2. It turns out the nonmetals are a lot more fickle, though. There's only 2 of them that we can count on. Oxygen, for the most part, always goes -2. It's in group 6. And in group 7, fluoride always goes -1. I'll put the noble gases out here. They don't play, they're always 0. But it turns out that whenever oxygen is in a compound, 99.9% of the time it's a -2 in its charge. There's only a couple exceptions to that. One is when it's called a peroxide, and it has a -1 charge. And that oxygen's kind of wound up. It likes to steal more electrons and become a -2. But as a peroxide, it's -1, and there's rare instances where it shows up in a homework problem. But I'll always warn you that that's coming. Now, fluorine, on the other hand, 100% of the time, in any tug of war over electrons, fluorine always wins because it's got the highest electronegativity of any element on the table. So consequently, when fluorine's in a compound, it's always going to be -1. Now that's the rub. Everybody else, all the transition metals, all of these nonmetals over here, they have various oxidation states. It just kind of depends on who they're with in the compound. Now you can pretty much guarantee that they're probably going to be with one of these group 1 or group 2 cations, and probably also an oxygen, because oxygen's pretty ubiquitous. It shows up everywhere. All right, well, let's look at assigning oxidation numbers to elements within a compound. All right, well, I mentioned to you that the transition metals and a lot of the nonmetals can be pretty fickle in terms of what charge they might adopt depending on what kind of compound they're in. For instance, manganese. Manganese can be a +2, a +4, a +5, a +6, or a +7, depending on what situation or what compound it's actually in and how much the other players in that compound tug on its electrons. For instance, in this compound, MnO2, it turns out that the manganese is in its +4 state. And I know this because oxygen, like I said, 99.9% of the time is a -2 whenever it's in a compound. All right, so if I know this one for sure, -2 each, I know that the sum of the oxidation numbers in a compound has to equal 0 if it's a neutral compound. So in this case, the manganese is +4. The name of this is actually manganese Roman numeral 4 oxide. All right, well, another example of a manganese compound, though, is this compound, KMnO4. This is called potassium permanganate. It's a mild oxidizing agent. I may have mentioned it in an earlier lecture. It's the purple stuff that we put in the lake. Well, let's look at the oxidation state of the manganese here. Now, see, it's hanging out with some elements whose oxidation numbers we know for sure, because potassium's a group 1 cation, so I know in a compound it's +1. And oxygen, like I said, it's -2 each all the time. Well, that means the oxygens, the 4 oxygens are -8, the potassium's a +1. Well, it's not too hard to figure what the missing number has to be. This has to be a manganese in its +7 state for that to add up to 0. So you can see that the game that we're playing. Generally, there's going to be some variable oxidation state player right here in the middle of the compound. But it's usually hanging out, like I said, with either oxygens and some group 1 cations or oxygens and some group 2 cations that we know for sure. And so consequently, it's not, too big a problem to deduce what the oxidation state of that central element is. All right, well, let's do a couple more. For example, a couple of compounds that we're familiar with. Sodium sulfate shows up from time to time, and its counterpart, sodium sulfite. Now, in this case, when you look at the oxidation state of the sulfur that's in the middle, you see this is a case where oxidation can be in 2 different oxidation states. Like I said, a lot of the nonmetals do this. Well, in sodium sulfate, the oxygens being -2 each would make this -8. The sodiums are +1 each, that's +2. Well, that implies that sulfur has to be in its +6 state. Now think about this. Sulfur's in group 6. It's got 6 valence electrons. Normally, you'd think that it would try to gain some electrons, but it's in a compound with oxygens. Oxygen's much more electronegative. Consequently, it overwhelms the sulfur, kind of pushes it against the wall. As a matter of fact, sulfur only had 6 valence electrons to lose control of, and apparently it lost all 6 of them. This is why you won't see sulfur in any oxidation state above a +6, because that pretty much maxes it out, whatever its group number is. However, sodium sulfite, if you notice the oxygens being -2 each, I'm sorry, this was supposed to be an SO3. Think of that as an SO3 right from the beginning. This is sodium sulfite. At -2 each, that's only -6 charges for the oxygens, still +2 for the sodiums, which puts this sulfur in its +4 state, not its maximum oxidation state. Now here's what's kind of interesting. If you leave this, a jar of sodium sulfite, open in the air, it will actually begin to oxidize or go bad because the sulfur is not at its maximum oxidation state. It actually will oxidize to a sulfate. But the sulfate, once it reaches that point, it won't oxidize any further. The sulfur is already at its maximum oxidation state. And so the reactivity of the sulfite is a little bit more so than the sulfate. And again, it's because of that oxidation state. As a matter of fact, let me show you another example. If we were to look at something really simple like sodium chloride. Now here's a case where a simple, binary compound with a cation and an anion, the sodium clearly is +1 and the chloride's -1. But when you put sodium in the compound sodium hypochlorite with an oxygen in here, it turns out the oxygen beats out the chlorine for the electrons and becomes the -2. The sodium can't do anything but be +1. This forces the chlorine to not do what it normally would like to do, and that's gain an electron. In this case, it loses control of an electron to the oxygen. Consequently, this chlorine is not particularly happy. It wanted to gain an electron, and in the process of making this compound, it lost one. Well, this is the main component in Clorox bleach. This steals electrons. It's a mild oxidizing agent. And you understand why, because the chlorine's kind of wound up. It wants its electron back. Actually, it wants 2 electrons, so it can become a chloride. All right, so you got a gravy stain on your shirt. We pour a little sodium hypochlorite in there. It starts stealing electrons from the covalent bonds holding the gravy together, breaks it up into little pieces, makes it more washable so you can get it out of the fabric. All right, and it's not so strong an oxidizing agent that it's going to eat your shirt, although if you put too much in there, it will. Now, if we put another oxygen, sodium chloride, NaClO2, here the chlorine's in its +3 oxidation state, much more wound up than the +1. As a matter of fact, this was sodium hypochlorite, this is sodium chloride. You can't use that in your washing machine. It would pretty much, all you'd find is buttons and zippers after that. If you go to NaClO3, this is sodium chlorate. The chlorine's in its +5 oxidation state, and it's mighty wound up. And I always tell people, if you put this in your washing machine, now you can't find the agitator and most of the tub is gone. But if you use sodium perchlorate, ClO4, now you can't find the washing machine and the wall to the laundry room's been damaged. Well, that's because the chlorine's in its +7 oxidation state. Again, you can figure that out by how many oxygens is there and the sodium's charge. Well, you push the chlorine to the wall now. It only had 7 valence electrons, and it was a mighty electronegative element, and now you've really pushed it backwards all the way upstream against the wall. This is why perchlorate compounds are so notoriously explosive. So you can see then that assigning oxidation numbers in a compound is really not all that tricky if you understand the simple rules about the group 1, the group 2 elements. Now, one thing I didn't put up when I said this about the rules is that any element, just in its elemental state, would have an oxidation state of 0. For instance, sodium as a solid would have an oxidation state of 0. Oxygen gas, O2 as a gas, it's got an oxidation state of 0. But once these elements enter into a compound, it's generally because they have either lost or gained electrons and become cations or anions. All right, so with that in mind, let's look at balancing oxidation-reduction reactions. Okay, well here's the fundamental idea of balancing reactions by looking at the electron exchange that's involved. I mentioned that in oxidation-reduction reactions, it's a transfer of electrons. Something loses the electrons, the species that's oxidized. Something gains them, that's the species that's reduced. So if I were to show you just a simple net ionic equation, for instance, like magnesium solid, if I were to drop a little chunk of magnesium into a solution that had aqueous aluminum ions, it turns out that magnesium is more reactive than aluminum and would much prefer to be in its ionic state, so they actually change partners. All right, well, the magnesium ends up becoming its stable ion, its +2 ion, and the aluminum accepts the electrons from the magnesium and gets reduced from its +3 state down to its 0 state, its solid state. Now, if you look at this equation, it's balanced. I mean, just by head count, there's a magnesium on each side of the arrow, and there's an aluminum on each side of the arrow. But the problem with oxidation-reduction reactions is it goes one step further. Not only does it have to balance by head count, but the total number of electrons lost by the species being oxidized has to be balanced by the total number of electrons gained by the species being reduced. Well, if that's the case, if we looked at the magnesium, let me just draw some arrows right here. This is my oxidation, what we call an oxidation half reaction. And this oxidation shows a loss of 2 electrons. However, my reduction reaction, and here the aluminum went from its +3 state down to its 0 state. In that case, this reduction had to represent a gain of 3 electrons. Well, there's where the rub comes in. Even though this is balanced by head count, the total number of electrons lost, 2 by the magnesium, are not balanced by the gain by the aluminum. Well, you see where this is going. To get rid of this imbalance, to resolve that, we're going to have to bump this up to the lowest common multiple of 3 and 2, which would be 6. So what if I were to triple my oxidation half reaction and double my reduction half reaction? So in that case, if I wanted to double or triple this, I'd need to put a 3 in front of the magnesium and a 3 in front of the magnesium +2. So that would represent 3 magnesiums, each losing 2 electrons, for a total loss of 6. And I'd have to double the reduction and put a 2 in front of the aluminum aqueous +3 ion and a 2 in front of the aluminum solid. Now notice that the total number of electrons gained and lost now are equal to one another, and I didn't mess up the head count, because each time I took a multiple of the half reaction, I balanced it on both sides. So the head count now balances, but in addition, the electron exchange balances. Now, when you get more players involved, this can get a little bit complex. And so let's look at taking this up just a notch. Okay, balancing oxidation-reduction reactions. There's 2 methods. In section 20.2 of your text, they discuss what's called the half reaction method. This is where you separate the 2 half reactions, you balance them separately. They have you add hydrogen ions, hydroxide ions, waters, and then add everything back together. It's a huge mess. It was actually invented by Satan. We are not going to do this method. So if you find yourself accidentally reading section 20.2, just avert your eyes. What we're going to use is the oxidation number method. This leaves the equation intact. You can balance it as is. I think you'll find this a much more preferable way to do things. Now, the oxidation number method, we're going to apply it to molecular equations where all the players are in place, and we're also going to look at net ionic equations where we've eliminated the spectator ions that are in there. The rules are subtly different when you do the net ionic equations. But let's start with an example of balancing just a molecular oxidation-reduction reaction. Okay, so here's a nice molecular equation that's an oxidation-reduction reaction. And I've written for you here the 4 steps in how to do this by the oxidation number method. First step, let's assign oxidation numbers to everybody that's in the equation. Now again, remember the rules are simple. Group 1 elements in a compound are +1. Group 2s are +2. Oxygen's always -2. Fluoride's always -1. With just those little simple guidelines, we can assign oxidation numbers to everybody here. Because in Fe2O3, the oxygens are -2 each. So this would be -6 charges. Well, that means that these 2 irons have to make up the other +6 charges, which would imply that this is iron +3. All right, so we've got an iron +3. We've got oxygen in its -2 state, -2 each. Actually, let me be consistent. I always put the each charge below and the total above. So there'd be +6 total charges here for the 2 irons and -6 for the 3 oxygens. So again, the oxygens were -2 each, the irons were +3 each. In carbon monoxide, now in this case it's not an ionic compound, but these are oxidation numbers. These are the oxidation states of the elements. Who's got control of the electrons? Well, the oxygen always wins here. It's going to be -2, which implies then that this carbon has to be a +2 carbon. Well, on the other side of the arrow, the iron is in its solid state. It's in its 0 oxidation state, so it has an oxidation number of 0. And the carbon that's in the carbon dioxide is actually in its +4 state, as these oxygens are -2 each. Okay, so does everybody see how we did the oxidation numbers? Not very difficult. I'm going to erase these each numbers because they're just going to get in the way. Now that we've established what the charges are on everything, we know that this is iron +3, and that this was iron 0, this was carbon +4, and this was carbon +2. So, step 2, we've identified the oxidized and reduced species. It looks as if the iron went from +3 down to 0. Well, that's a reduction in charge. Well, it got reduced. On the other hand, the carbon got oxidized. It went from +2 up to +4. Now, once we've identified them, I always write this little addendum in here that if you need to pre-balance your oxidized and reduced species, do that now. Because you'll notice we've got 2 irons coming in the front door and only 1 iron leaving out the back. Well, ultimately, I know that there's got to be an equal number of irons on both sides. So we need to start with an even level playing field. Let's at least double the irons on this side so that we know we've got 2 on each side to deal with. If we have to bump that up by a factor, then at least we're starting with an equal number on both sides of the arrow. So I'm going to start off with a 2. All right, so here's how we begin. We need to balance the electron exchange. That's step number 3. Well, the irons got reduced. I always put my reduction arrows on the bottom and my oxidation arrows on the top. It looks as if these 2 irons at +3 ended up being these 2 irons at 0. Well, that means each of those irons gained 3 electrons to do this. So right now, currently, as it's written, this reduction represents a gain of 6 electrons. On the other hand, the carbon went from +2 to +4. This is my oxidation. I'm going to draw arrows up here and say, all right, well, that's an oxidation with a loss of 2. Well, the rule says that the number of electrons lost should equal the number gained. So apparently, I need to resolve this by tripling the oxidation half reaction. All right, well, if I triple that, that simply means that I need to put a 3 in front of the carbon monoxide and a 3 in front of the CO2. Now at that point, I do have 6 electrons being lost, 6 electrons being gained. So the hard part's over. I've balanced the oxidation reduction part of this reaction. If there were any remaining players, like some water molecules, for instance, we might have to balance some remaining mass. In this case, everything already clicked. You'll notice that it's balanced exactly. All right, well, I put step 4 here just in the event that there were some leftover loose ends that we needed to balance. Now, as long as we balance them without screwing up the coefficients we put in front of our oxidized and reduced species, we're good to go. All right, well, let's take a look at, 200 or 300 more examples of this. Okay, so here's a nice molecular equation. Potassium chlorate reacts with the hydrogen bromide, hydrobromic acid, makes bromine as a liquid. I didn't put the phase notations in here, but it makes bromine as a liquid, and potassium chloride and water. Now, this is an oxidation-reduction reaction. There is a loss of electrons and gain. So again, the first step is let's assign oxidation numbers to everything that's here. Well, in potassium chlorate, remember group 1 cations, always +1. So +1 each, that would be +1 then for the potassium. -2 each for the oxygens would be -6 for the oxygens, which, if we're looking for the missing number, the chlorine's going to have to be a +5 for this to balance out to 0. All right, so I'm going to get rid of these each numbers down here because it just makes things messy now that we've got the totals up there. So the chlorine was at +5. In hydrogen bromide, the hydrogen's a +1 and the bromide's a -1. In bromine, when bromine is in its neutral state as an element, it's 0. They're just sharing electrons. They haven't lost or gained any. And the potassium chloride, potassium's a +1 cation, chloride's a -1 anion. And remember, water is pretty ubiquitous. It shows up in a lot of these different equations, and whenever it does, it's usually not a player. The hydrogens are +1, the oxygens -2, so this is a +2 -2 situation right here. And again, you'll see water appears in a lot of these equations. All right, so there was our first step, assign oxidation numbers. Now, if you find down the line that you can't get an equation to balance, that you hit a dead end and it's just not working, chances are you misassigned an oxidation number. Go back to step 1. That's where the mistake happened. All right, so we've got our oxidation numbers, and it's pretty clear then if we want to identify who got oxidized and reduced, it looks like the chlorine changed. It went from +5 all the way down to -1. Now think about that. That's a gain of 6 electrons to go all the way from +5 down through 0 all the way to -1. And it looks as if the bromine's changed. The bromine here is a bromide. It went from -1 to bromine at 0. Now remember I said once you've identified who got oxidized and reduced, let's pre-balance this a little bit. We know there's gonna be an equal number of bromines on both sides. So I'm gonna at least start off by making sure that there's an equal number of them on both sides. I'm gonna double this. Now granted, later we may have to bump both of those up by a factor, but at least we're starting with an equal amount on both sides of the arrow. All right, well, let's draw our arrows for our oxidation and our reduction. In this case, the oxidation was actually the bromine, the bromide. Now, the way the equation is currently written, with 2 bromides at -1 each going to 2 bromines at 0, each of them had to lose an electron. So this oxidation right now currently is a 2 electron loss. The chlorine, on the other hand, went from +5 all the way down to -1. And as I mentioned before, that's a reduction and a gain of 6 electrons. Well, here's step 3. It says make sure that this is balanced, that this, if there is an imbalance here, resolve it. Well, to do that, it's pretty clear. I'm going to have to triple my oxidation half reaction. Remember, these reactions are always made up of 2 half reactions, an oxidation half and a reduction half. Well, in this case, the oxidation half is going to have to be tripled in order to be right there. All right, well, let me triple that. That means now I'm going to have to bump this 2 that I played here, that pre-balancing 2, up by a factor of 3. This is going to go up to 6. This is going to go up to 3. So again, I just took whatever numbers were there and I bumped them both up by a factor of 3 to make this equal. And again, 6 electron loss now, 6 electron gain. All right, well, step 3 is done. So the hard part's over. I've got the oxidation reduction part of this balance. Now, just any loose ends, I got to tie them up. Well, it appears like the only place I can play numbers without affecting what I've already done is in front of the water. because I'm married to these numbers now. The implied 1 in front of the KClO3 and the KCl, and this 3 and 6 are carved in stone now, because I can't upset the card here with my oxidation reduction. But I can play a number in front of the water, won't affect anything. Well, it appears that I have 6 hydrogens now on this side of the arrow, and the only place those 6 hydrogens seem to be going out the back is in the water molecules, which means a 3 here should balance those hydrogens. Now usually then, I leave the oxygens till last, because they're slathered all over the equation. Hydrogens next to last, oxygens last. That's usually what happens in these equations. Well, I've got 3 oxygens on this side, and apparently I now have 3 on this side with the 3 waters. So bingo, it's balanced. The head count's balanced, but underlying that, the electron exchange was balanced. All right, well, let's try another. Okay, here we go again. Another one, not too tough. Nice molecular equation here. Nitric acid, hydrogen sulfide. It reacts to make nitric oxide, NO, and solid sulfur as a powder, and water. Generally, if you run this at a high temperature, the water comes out as a vapor. Again, I left the phase notations off because this gets so messy with all the numbers we put on here. But let's assign oxidation numbers first. Now again, HNO3, hydrogen's a +1. The oxygens are -2 each, so this is -6. That means that nitrogen is a +5. Now, after you do a few hundred of these oxidation reduction reactions, you realize that every time I came across a nitrate, that polyatomic ion, the nitrogen was always a +5. Well, that kind of makes sense, doesn't it? Because if the nitrate ion itself is a -1, that means the oxidation numbers of these two elements have to add up to equal -1. And we know that this is always the case with a nitrate. It always has that charge, which means the nitrogen would always have to be a +5 in a nitrate group. So whenever you see nitrate groups, after a while you realize, oh yeah, that nitrogen is a +5. Okay, well, I get rid of that. In the hydrogen sulfide, the hydrogens are +1 each, so that's +2. The sulfide then must be the -2 form of the sulfur. In nitric oxide, where the nitrogen is just with 1 oxygen, remember that oxygen's -2, so that means this nitrogen is a +2. Here, sulfur in its elemental state, no charge, all by itself, it's a 0. And water, again, is just a +2 -2 arrangement between the hydrogens and the oxygen. Okay, so we've assigned oxidation numbers. Let's identify our oxidized and reduced species. And if there is any imbalance there between them, we'll do a little pre-balancing. I don't think we need to in this case, because the nitrogen appears to be our reduction. It went from +5 down to +2. And there's only one of them. So here's our reduction. Our oxidation looks like it's the sulfide. Went from -2 to 0. Notice no one else changed in oxidation state. So here's our oxidation. We don't need to pre-balance because I have 1 sulfur here, 1 sulfur here, 1 nitrogen, 1 nitrogen. So at least we're comparing apples to apples here. All right, well, my reduction from +5 down to +2 was a gain of 3 electrons. But my oxidation of the sulfur from -2 to 0 was just a loss of 2. Well, again, this is where we have to balance the oxidation reduction part of the reaction. And the way to resolve this is to triple the oxidation half reaction and double the reduction half reaction. All right, so I'll take this times 3, which means I have to put a 3 in front of the H2S and a 3 in front of the sulfur. So I tripled my oxidation half. The reduction I'm going to have to double. So that means 2 HNO3s are coming in the front door and 2 NOs are going out the back. All right, so now we've balanced the electron exchange. And we are now married to these numbers. Those 2s and 3s that I just played to balance that, I can't alter those. I can't change them. But they did leave me one last spot. I could play a number that doesn't affect the oxidation reduction. And this is just to tie up the loose ends. Again, the hydrogens and the oxygens. So I usually look at the hydrogens. I leave the oxygens till last. Well, look here, I've got 2 of them here with the nitric acid. I've got another 6 here with the hydrogen sulfide. So I've got 8 hydrogens to account for, and it appears the only place they're going out the back is right there with the water again. Well, 4 waters would give me my 8 hydrogens. Let's hope that the oxygen's balanced, because I'm out of place here. Well, I've got 6 oxygens on this side. Appears there's 2 here, 4 there. There's my 6 oxygens. Bingo. All right, so we've got it balanced according to head count. We did that at the very end. But the most important part was the underlying oxidation reduction part. All right, well, let's crank this up a notch. Let's get mean. Okay, here's one I couldn't even fit on the board. So anyway, here's our reactants: potassium permanganate, potassium chloride, sulfuric acid. It reacts to make manganese sulfate. This is manganese Roman numeral 2 sulfate. I know that because I know that a sulfate group is always -2. So that, again, makes the manganese a +2. And what's also going to make potassium sulfate, chlorine gas, and water. All right, well, this one, you can see there's a lot of players. So this gets a little more interesting. All right, well, let's assign oxidation numbers. Potassium in the potassium permanganate, back down here, is a +1. Well, the oxygens are -2 each, so that's -8. That makes this manganese a +7. I'm going to go ahead and just put its number there because I know the potassium isn't going to change. Neither is the oxygen. All right, in the potassium chloride, the potassium's a +1 and the chloride's a -1. That's just a binary salt, common ionic charges on those. Sulfuric acid, the sulfur in there, the hydrogens are +1 each, so that's +2. This sulfur is a +6, and the oxygens -2 each is -8. Again, I know the sulfur in a sulfate group is always +6, just because after you do a few hundred of these, you realize a sulfate group has a -2 charge. For that to have a -2 charge, this sulfur has to be a +6 because of the -8 of the 4 oxygens. So regardless of who it might be with cation-wise, in a sulfate group, internally, the sulfur has to be a +6. Okay, so on the other side of the equation, I see that, again, here's a sulfate group. That's what led me to believe that this manganese is a +2. I'm not going to even bother assigning the oxidation numbers to the sulfate because it clearly hasn't changed. It was a sulfate group here, it's a sulfate group here. Oh, and here it is again as a sulfate group. As long as the sulfur didn't change in its oxidation state, then it's not a player in the underlying redox game. All right, so in that case, the potassiums here are +1 each. Again, the sulfate is a -2. That's a sulfur with a +6. So again, of no interest to us because it stayed a +6 all the way through. The chlorine, however, changed. It started off over here as a -1, but here in its elemental state, it's a 0. All right, so again, there's an oxidation force because the chloride had the electron, the chlorine doesn't. And in water, again, it's just a +2 -2 arrangement. Okay, so we've identified then, step 2 is identify the species that are oxidized or reduced. Well, it looks as if the manganese is a player. It went from +7 down to +2. Oh, let me duck down here. I'm going to go ahead and put our arrow down here. It appears that here's our reduction. Well, our oxidation was what I mentioned before, the chloride. Now, at this point, here's the oxidation down to the chlorine. I'm going to pre-balance here, again, because I want to start with an even playing field. I've got 1 manganese on each side. But right now, I have 2 chlorines on this side because they have to leave in pairs. It's a diatomic element. So I need to start at least by doubling the KCl that was here. All right, well now a 2 in front of the KCl means that there were 2 chloride ions that became these 2 chlorine atoms, each losing 1 electron. So as the equation is currently written, there's a loss of 2 electrons. Now granted, I may have to bump that up by some factor depending on what happens down here. As a matter of fact, our manganese going from +7 down to +2, this is a gain of 5 electrons. All right, now that's an imbalance. We've got a reduction by 5 and an oxidation of 2. The only way to resolve this imbalance is to take this up to a common multiple of 10. So we're going to have to take the oxidation half reaction times 5, which means a 5 in front of the chlorines. It means now a 10 in front of the KCl. Let me get rid of their charges here. A 10 in front of the KCl, and again, that would account then for a 10 electron loss. Each of those chlorines losing 1 electron. We need to double the reduction half reaction. So a 2 in front of the MnSO4 and a 2 in front of the KMnO4. All right, well, if that's the case, then now again, I'm married to those numbers. Those 2's that I placed there to give me a 10 electron gain, and this 10 and 5 that I played in order to give me a 10 electron loss, I have to not touch those numbers. All right, but we need to tie up a lot of loose ends here. You'll notice, though, that I've got a couple players that aren't in the redox part of the reaction. The potassium sulfate I can use to balance, and the waters I can use to balance, tie up, again, any loose ends. I'm getting rid of these numbers just because it neatens things up a little bit, or charges. Okay, well, let's look, for instance, at how many potassiums. Notice that we're kind of locked in to the potassiums on the left side of the arrow. That these 10 I'm married to, and these 2 likewise. Well, that's 12 potassiums. I only see them going out one place on the other side of the arrow. There's sulfates that are going out everywhere, but the potassiums, definitely, I'm locked into those 12 potassiums. I'm going to put a 6 in front of the K2SO4 just to account for the 12 potassiums on the left side of the arrow. All right, well, now that pretty much ties me in then. If I'm married to that 6, now I've got 6 sulfate groups. I can just treat them as one big chunk. 2 more sulfate groups here. That's 8 sulfate groups on this side. And there's only one place that sulfates are coming in on the left side of the arrow is with the H2SO4. I'm going to have to play an 8 there. All right, now, 8 sulfuric acids. And don't be surprised when these numbers get a little bit large. With oxidation-reduction reactions, when there's a lot of players involved, sometimes you can get coefficients that are pretty big, so don't let that throw you. All right, well, we've got our sulfates balanced. I think we're down to just the water. That's the only place that I've got anything left to play, and the hydrogens and the oxygens aren't balanced yet. As a matter of fact, on this side, I'm seeing 16 hydrogens, and the only place that those hydrogens are going out is here with the water molecules. Well, 16 of them would be enough to make 8 waters. Well, let's hope that the oxygen's all balanced, otherwise we're painted into a corner. Well, I've got 8 oxygens here. I've got 32 oxygens there. I've got 40 oxygens on this side of the arrow. Well, let's see if I've got 40 on this side. There's 8. Here's 6 times 4 is 24. That's 32. Oh, there's 8 more. That's 40 oxygens. Hot dog. All right, so you can see that when you get a lot of players here, you got to be careful. If you get down to the end, like I said, and this thing will just not balance, chances are you misassigned an oxidation number right off the bat. So go back to step 1 and look at it and see what your oxidation originally lost and what your reduction originally gained. Usually that's where the mistake's made. All right, well, I want to show you a couple that are on the pre-lab, and then we need to talk about how to balance the net ionic oxidation-reduction reactions. I couldn't resist. I found another really good one in a book. This is potassium dichromate. Let me duck down a little bit here. Potassium dichromate hydrochloric acid to make potassium chloride, chromium 3 chloride, water, and chlorine gas. Now you notice there's chlorines going everywhere in this thing. and they're all coming from the HCl. But as we assign oxidation numbers, something gets revealed here. Now, first off, going through potassium dichromate, the potassiums are +1 each. So that's +2. The oxygens are -2 each. That's -14. That means together these two chromiums are +12. That makes this a chromium +6, right? Each of them would be +6 in order to make up the +12 necessary to make that balance out to 0. The hydrochloric acid, the hydrogen's a +1, the chloride's a -1. On this side, notice that the chloride here is still a -1. The potassium's a +1 because it's a group 1 cation. All group 1 cations are +1. Chromium chloride. Well, if this is still just a binary salt, that chloride is still just a -1, and there's 3 of them. So that means that this chromium's a +3. Well, then apparently the chromium must be a player because it started off as a +6 and ended up a +3. The waters, +2, -2. I mean, that's usually the case, that they don't usually change. The chlorine, on the other hand, now notice that chlorides showed up over here quite a bit. But there's a couple chlorines that ended up being 0. Now this implies then that since the chlorines are only coming in here with hydrogen chloride, some of them are just along for the ride. There's going to be some HCl's here that ended up in the potassium chloride and did not change. And there's some chlorides that ended up here in the chromium chloride that likewise did not change. But I know there's at least 2 of those guys that ended up here that ended up at 0. So in cases like this, where there's an element that is involved in the oxidation reduction, but in addition, there's another pile of them that are just along for the ride, I literally make 2 piles of them. One to be involved in the oxidation reduction, and one to just ride along. So here's what I'm going to do. I'm going to put 2 piles of HCl here. And I'm going to say that 2 of them ended up being my, oh, actually, let me put them up above. Those 2 chlorides that are there that are -1 each are the ones that are going to become my oxidation, to become these 2 chlorines. These HCl's that I'm leaving down here in my second pile, I'm going to let them be the ones that I'm going to use to balance with the other chlorides that are involved. And when the dust all settles, I'll add the 2 piles back together. But at least I'm going to separate 2 of them to be part of the oxidation. Well, the reduction is the chromium. Now remember, we have to do a little pre-balancing here because I'm starting with 2 chromiums on one side and only 1 on this side. I know I'm going to at least have to have 2 here to make the chromiums balance. Again, this may have to be bumped up by a factor, but at least I'm starting with an equal number on both sides. Now notice something. If each of them went from +6 down to +3, that means each of these 2 chromiums gained 3 electrons. So the way this is currently written, this is a reduction and a gain of 6. The 2 chlorides that were here that were -1 each and became these 2 chlorines, each lost an electron, so this is only a loss of 2. All right, well, we can resolve that. All we need to do is triple our oxidation half reaction to balance out these 6 electrons in the reduction. Well, if I triple that, that means a 3 in front of the Cl2. This 2 HCl now becomes 6, because that way 6 of those chlorides lost an electron to become these 6 chlorines. So sure enough, there's a 6 electron loss and a 6 electron gain. Now I'm married to that 6 in this pile of HCl's, but that doesn't mean I can't add additional HCl's that are just along for the ride. All right, well, as a matter of fact, let's start off with the potassiums. we're kind of married to this implied 1 out here in front of the potassium chromate. So those 2 potassiums only end up here. I'm going to go ahead and put a 2 here just to balance the potassiums. Now this 2 I'm married to, right? Because that's part of the oxidation reduction. The only place left that I can play a number is in front of the HCl's that are along for the ride and in front of the waters. Well, let's take care of those other chlorides. Notice that there's 2 of them here with the KCl. There's 6 more right here in the CrCl3. So that's 8 chlorides that ended up still being chlorides. That's not counting the ones that were involved in the oxidation reduction. So there's 8 HCl's that are necessary here in order for those 8 chlorides to become these 8 chlorides. So in essence then I had a total of 14 HCl's here. 6 of them actually got oxidized. The other 8 were just along for the ride. All right, well, we still have one thing left to play is the water. The hydrogens and the oxygens aren't balanced yet. All right, well, the hydrogens only came in right here, and apparently there's 14 of them. Well, 14 of them, and the only place the hydrogens end up is there in the water. Well, 7 waters will take care of 14 hydrogens. If the oxygen's balanced, then we know we did it right. All right, well, I've got 7 oxygens on this side. Well, dang, there they are in the 7 waters. Everybody else is balanced, and now the oxidation and the reduction is also balanced. Now you can understand, with an equation like that, that might be mighty tricky to balance if you just looked at it by inspection. If you didn't look deeper at the oxidation numbers, just trying to balance the head count would be tricky with this one. But once you dig a little deeper and you look at the oxidation numbers and get that little part of the reaction balanced, then the rest of it falls into place. All right, I got a couple more that I found here in the book. I'm going to keep going. Oh wait, one last thing. Remember I said you could add these back together. So in essence, we could just make this 14 HCl's. Again, we know that only 6 of them were involved in the oxidation reduction. So I'm sorry, I skipped that very last little step. All right, now our next problem. Okay, this one allows me to show you something about nitrogen. It shows up in a lot of equations because of the commonness of the ammonium ion. You see this a lot because it's a pretty common salt to pair up with some anion. Well, when you look at that, you get in the habit of always having the positive part first and the negative part second. But in the ammonium case, that's not the case. The hydrogens are still +1 each, which means that would be +4. Well, for this to add up to be a +1, that nitrogen has to be in its -3 state. All right, and so that's always a little bit, a little bit hard to discover when you're first learning about oxidation reductions, is that the nitrogen in ammonium or in ammonia, NH3, which we looked at in the Haber process, the manufacture of ammonia, the nitrogen, again, is in its -3 state. Okay, so keep that in mind because there's one like that in your pre-lab. I'll show it to you in a little bit. All right, well, let's assign oxidation numbers here like we always have. The zinc is in its 0 oxidation state. HNO3, now here's something to look at. When you first look at this equation, you see that there's nitrate groups here. And like I mentioned before, after a while you get to recognize that the nitrogen in a nitrate group is a +5. So that means these nitrate groups are of no consequence because nitrates are nitrates, they didn't change. And as a matter of fact, there's a nitrate down here. However, there is a nitrogen right here in the ammonium that, remember, is not a +5. Like I just mentioned, it's a -3 because of the 4 hydrogens being +1 each. If this nitrate group is a -1 in its totality, then this nitrogen has to be a -3 nitrogen. All right, well, then the nitrates are just along for the ride, except for one of them has to end up here. Well, if that's the case, then I think I'm going to make 2 piles of HNO3. just like we did in our last example, I'm going to let one of them just go along for the ride and make up these nitrates and that nitrate. But there's one nitrogen I know ends up here as a -3, and it started off as a +5. So did this one. Okay, so on the other side of the arrow, assigning oxidation numbers, this zinc is in its +2 state. Again, I know that because it's linked here with an anion, and nitrate has a -1 charge, that anion, and there's two of them. That's zinc +2. The water's not a player, but it does help us balance the mass later, and that's just a +2 -2. All right, so now we can identify who got oxidized and who got reduced. And we've kind of taken care of our pre-balancing. We've at least isolated one HNO3 to end up here with this nitrogen, and we've got one zinc on each side, so we're good to go. All right, well, our oxidation, sure enough, is the zinc. Loss of 2 electrons. The HNO3, this one anyway, will count as our reduction. Now think about it, it went from +5 all the way down to -3. To do that, that's a gain of 8 electrons. All right, well, here we go. Now we've identified the oxidized reduced species. We need to take care of this imbalance. We need to forple our oxidation half reaction. All right, so if we forple this, that means a 4 in front of the zinc nitrate and a 4 in front of the zinc metal that we started with. So now we're tied to that 4, and we're tied to this 1 and this 1 that's in front of the HNO3 that became this NH4NO3. Well, that's kind of nice because that has locked us into the total number of nitrate groups that were just along for the ride. We've resolved the electron imbalance. So now that we're just tying up loose ends, it appears that the other pile of HNO3s that we had that were just going to, again, be along for the ride, made up these 8. Remember, we got a 4 out here in front. There's 8 nitrates there, and there's 1 that we're married to right there. There's 9 nitrate groups that ended up going along for the ride. So I'm going to put a 9 in front of that. So in essence, we had 10 HNO3s in the equation, but only one of them actually was involved in the oxidation reduction and became this nitrogen. The other 9 of them made up the other nitrates that are on the right side of the arrow. Now I think we can tie up the last loose end with the water, because we do have now 10 hydrogens to account for here. The only place they went out, there's 4 of them right there. So 10 in the front door, 4 accounted for, leaves 6 hydrogens unaccounted for. I think a 3 in front of the water will do the trick. Now, if the oxygen's balanced, we did it right. Well, we've got 30 oxygens here with those 10 HNO3s. 30 oxygens, and it looks like we've got, 6 times 4 is 24. There's 3 more is 27. There's 3 more is 30. 30 oxygens on both sides, so we got it. All right, so you can see that each one of these is its own little puzzle. Every time we put up an oxidation reduction reaction, first step, go through and carefully assign oxidation numbers to everybody. And again, if you need to do a little pre-balancing just to make sure you're starting off with equal numbers on both sides, that's the spot to do it. All right, well, let me show you a few that are on your pre-lab. I'm going to put a few of them on the board and at least give you a few little tips. Now, for today's lab experience, we're going to walk you through a titration, an oxidation reduction titration. The only thing I need you to turn in is the pre-lab sheet with the balanced oxidation reduction reactions on it. All right, so let me give you a few little tips on that. Okay, these are the first 3 equations that are on your pre-lab sheet. And the first one is really pretty simple. You can almost balance it by inspection and be correct. You've got zinc in a 0 state, silver with a nitrate in its +1 state. The zinc ends up +2 and the silver ends up 0. Once you balance the oxidation reduction part of this, it's pretty much over. There's no loose ends to tie up. So again, we start you off nice and easy to lull you into that false sense of security. They get a little bit more difficult as we go on though. Number 2 has tin in its metallic state. Let me get out of the way here. tin nitric acid going to tin oxide. Now remember the oxygens are -2 each. That will help you deduce the charge on the tin. It started 0. Notice the nitrogen here in HNO3 does change to NO2. This nitrogen is in its +4 state because of the 2 oxygens that it's with. So again, balance the oxidation reduction part of this. You'll need the waters to tie up the loose ends at the end of that. Number 3, or letter C, gets a little bit more complex. We've got MnO2. Again, I showed this one earlier. Easy enough to deduce what the charge on the manganese is here. PbO2, same way. Lead only comes as either a +2 ion or a +4. It's pretty easy to figure it's with 2 -2s. All right, and nitric acid. Now, I think that nitrates are just along for the ride in this case because they end up being nitrates on this side. It appears the manganese and the lead are the only players. The manganese definitely changed over here, HMnO4. I'll let you deduce the manganese charge. And the lead nitrate, remember nitrate's just a -1 anion and there's 2 of them. The water, again, you're going to use for tying up the loose ends. All right, that should give you enough hints to get through those first 3. Let me put the other 3 on the board and show you a couple little tricks. Okay, letter D. Now the trick here with zinc, sodium nitrate, sodium hydroxide to become this zinc complex and ammonia and water. The zinc clearly is a player because it starts off at 0 and it ends up in its normal +2 state on this side. It's the nitrogen in the NH3. I mentioned earlier that is in its -3 oxidation state. So there's your other player because it did not start as a -3 here in the nitrate. All right, I'll let you go ahead and deduce that one, but at least I wanted to remind you that the nitrogen's a -3. That's kind of the trick there. In whichever letter that was, letter E, potassium dichromate. Now, notice that I've got 2 chromiums on one side, 2 chromiums on the other, and they are players in this case. I'll let you figure out what the value is for the chromiums. But as it's written, remember that each of the chromiums is going to, I believe, gain some electrons because, well, you'll see when you assign the oxidation numbers. So remember that write your reduction for how it's currently written with 2 chromiums. Now, the sulfur that's involved here, notice that there's sulfurs in the hydrogen sulfide and there's sulfurs that's in the sulfuric acid. Well, these sulfates in the H2SO4 become these sulfates and are not really involved in the oxidation reduction part of the reaction. But you'll notice that there is another form of sulfur on this side of the equation. It's these two, the H2S and this sulfur, that are tied together for the oxidation reduction part. That should lead you to the correct balancing. Now, the last one, I really like this one because there's actually 2 oxidations going on with 1 reduction. Because the manganese turns out to have changed and has become oxidized, but the chlorides that are here with the manganese become these chlorines on this side. They likewise get oxidized. But at least they're tied together, so there's one bulk loss of electrons. It's just that when you have to bump that up by a multiple, you have to bump up all the participants in the oxidation by that same factor. So just keep your eye out for that. There's 2 concurrent oxidations going on with 1 reduction. And again, once you get that balanced out, you'll see that the loose ends are pretty easy to tie up. All right, well, I want to walk you through what we were going to have you do for the lab, but first, let's look a little bit at how to balance the net ionic redox equations. There's a couple extra steps here, and so for those of you who are in my lecture and not necessarily in the lab or vice versa, I wanted everybody to at least see this. Okay, before we actually do a net ionic redox reaction, the rules are subtly different, but the first couple are the same. The first thing to do is assign oxidation numbers to everything involved and identify the oxidized and reduced species and pre-balance them if necessary. Well, the next thing is exactly the same. We balance the electron exchange, the oxidation half reaction with the reduction half reaction. Here's where things change. In these types of net ionic equations, they tell you that they're running them either in an acidic solution or a basic solution. So they want you to balance the ionic charge, meaning total up the positives and negatives on both sides of the arrow. they have to be equalized. If the net amount of charge coming in on one side actually has to be balanced with the net amount of charge going out on the other side. Your currency for balancing this charge are the hydrogen ions for those equations done in acidic solution. So you can feel free to add hydrogen ions to either side of the arrow that's necessary to balance out the ionic charge. If the equation is run in a basic solution, you're allowed to add hydroxides to either side. Now remember, back in the molecular equations, we didn't add anything. Everything we needed was there already. In the ionic equations, we get to add hydrogens or hydroxides depending on what media they told us they were running the reaction in. And again, this is in order to balance the ionic charge. In addition, when they do the last step and balance the remaining mass, you're allowed to add waters if necessary to make up for your additions of hydrogens and hydroxides. So unlike the molecular equations, we actually get to add things at the end to make sure that everything balances out. All right, well, let's do several examples of this and I'll show you what I mean. Okay, well, let's look at one of these net ionic equations. Actually, I'll do two examples in acidic solutions and then I'll do a couple in basic solutions, and then we'll get on with this lab experiment and get this over with. Now, in acidic solution, again, remember later we can add hydrogen ions to either side of the equation we need to in order to balance the charge. But let's do our first step. Let's assign oxidation numbers. Now, in the NO3 minus, the nitrogen is in its +5 state. The oxygens, again, are -2 each. Note that this is a net ionic equation and the unnecessary spectator cations have been eliminated. So now the oxidation numbers have to add up to equal the charge on the species. So in this case, with the -6 for the 3 oxygens, this would have to be a +5. The copper in its elemental state is 0. The nitric oxide, NO, with 1 oxygen at -2, this nitrogen has to be +2. And in this case, they've indicated that we've got an aqueous copper +2 ion. Again, its anion has been eliminated as a spectator ion. All right, well, I think we've identified who got oxidized and who got reduced. I'm going to erase this in acidic solution for a second, but remember, we're going to be able to add hydrogens here in a second. So the oxidation was right here. The copper went from 0 to +2, so that's a loss of 2 electrons. On the other hand, the nitrogen, and notice we don't have to pre-balance because we've got one of each and one of each on both sides of the arrow. The nitrogen went from +5 down to +2. So there's my reduction, a gain of 3 electrons. Okay, well, this is an easy imbalance to resolve. All we have to do is bump this one up by a factor of 2 and that one by a factor of 3. So let's double our reduction half reaction, meaning 2 NO3s and 2 NOs. Let's triple our oxidation half reaction, meaning 3 coppers and 3 copper ions. Okay, so we have resolved now the electron imbalance. So let me erase everything here. Oh, I'll find my eraser. Hold on just a second. All right, so we've resolved the electron imbalance. So I'm going to get rid of our reduction arrow and our oxidation arrow. And I'm going to get rid of the oxidation numbers up here. But what I'm going to leave are the ionic charges. The charge that's on the nitrate anion and on the copper anion. Notice everybody else was a neutral compound or an element. All right, well, if I look at the charges on both sides of the arrow, it turns out there's 2 -1 charges on this side. So there's 2 negatives on this side of the arrow, but there's 6 positives on this side of the arrow. Well, now that can't happen. The number of net positive or negative charges don't have to be eliminated, but they have to be equalized on both sides of the arrow. And our currency of charge are hydrogen ions because they dictated that this was going to be done in an acidic solution. All right, well, if I want to undo this imbalance, I need several positive charges on this side in order to bring it up to equal 6 positives. As a matter of fact, I'd have to add 8 positive charges on this side to make these two equal. Now the reason I have to add the positive charges again is because that's my currency, is the hydrogen ion. So I'm going to add 8 hydrogen ions with a +1 charge to give me 6 positive charges on this side of the arrow. So I'm going to add 8 H pluses on this side, plus the 2 nitrates, plus the 3 coppers, to go to the 2 NOs and the 3 copper plus 2s. Now suddenly, if I total up the net amount of charge on this side, ionic charges, there'd be 6 positives balanced by the 6 positives on the other side. Now, in addition to my ability to add hydrogen ions to whichever side of the arrow I feel is necessary to balance the charge, I can also now add waters to balance the remaining mass. Well, I'm going to have to, because those 8 hydrogens don't have any place over on this side of the arrow to go except for waters. So apparently with 8 hydrogens, I can have 4 waters. And magically enough, if I balance the hydrogens, the oxygens are going to balance. There's 4 oxygens there, 2 more here for a grand total of 6. Sure enough, there's 6 oxygens on this side of the arrow. So the only real twist in doing these is once you get the electron exchange balanced out, then you have to look at just the ionic charges. So erase all of your oxidation numbers and just look at the actual charge on the species. And if they tell you it's in an acidic solution, you can add hydrogens to whichever side of the arrow would equalize that amount of charge. Then add waters, whichever side you need to tie up any loose ends. All right, let's do one more in an acidic solution. Okay, here's another one in acidic solution. This is the dichromate anion. It's got a -2 charge on it. And the chloride ion, and these would both be an aqueous solution. Again, I left the phase notations off just so this doesn't get too messy. They actually have an oxidation-reduction reaction where the chromium becomes chromium +3 ions and the chloride becomes chlorine gas. Well, in this case, if we assign an oxidation number to the chromiums here, it turns out that they're in their +6 each state. You can figure that out because 7 oxygens at -2 each is -14. Well, to add up to -2, that means the 2 chromiums together have to be +12, which means that each of the chromiums there is +6. Those +6 chromiums are going to become these +3 chromiums, so there's our reduction. Our oxidation is the chloride becoming chlorine. So you'll notice, however, and the chloride, by the way, has a -1 oxidation number. The chlorine has a 0 oxidation state. So we need to do a little pre-balancing for both of them. Because right now I've got 2 chromiums on this side. I know that at least I got to have 2 on this side to start with. And again, I might have to bump that up by a factor, but at least start with an equal number on both sides. The chlorine the same way. I got to start with at least 2 chlorides just to start with an even playing field. All right, now I can look at the number of electrons lost and gained with the equation as written, knowing that these 2 chromiums at +6 became these 2 chromiums at +3, meaning that each of those chromiums had to gain 3 electrons, a total gain currently, the way it's written, of 6. Now remember, this is an acidic solution. Later we're going to get to add hydrogen ions and waters to this to make the charge balance. Okay, so here's our reduction. These 2 chromiums became these 2 chromiums, and each of them gained 3 electrons. So here's our reduction, currently with a gain of 6. The 2 chlorides at -1 became 2 chlorines at 0, meaning that each of them lost 1 electron. So there's my oxidation. Loss of 2. Again, nothing tricky here. We can resolve that imbalance by tripling our oxidation half reaction, which means this 2 now magically is going to become a 6. I bumped it up by a factor of 3, and I bumped this up by a factor of 3. So now we've got a total of 6 chlorides becoming 6 chlorines, each losing 1 electron. That's going to be our 6 electron loss, balanced by our 6 electron gain. All right, so the hard part's over. We've balanced the oxidation reduction part of this. But being that it's a net ionic equation and they told us it was being run in acidic solution, there's hydrogens involved in this. And we can figure out how many hydrogens are involved simply by looking at the total amount of ionic charge. So again, I'm going to get rid of all of the oxidation numbers and just look at the charges on the ions. So for instance, I had one dichromate ion, that's 2 negative charges. I had 6 negative chlorides for a total of 8 negative charges on this side of the arrow. On this side of the arrow, I've got 6 positive charges, 2 chromium plus 3s. The chlorine was 0, so 6 positives over here. Well, I have in my pocket hydrogen ions that are positively charged that I can add to either side of the arrow to equalize this. Not to eliminate it, but to equalize it. So I'm going to have to bring these negatives up to match these 6 positives. That means I got to add 14 hydrogen ions. 14 H pluses would add 14 positive charges to those 8 negative charges. That would bring us up to a net 6 positive charges on this side. But that means I have to add 14 H pluses on this side of the arrow. Can you see those? Yeah, 14 H pluses. All right, now in order to get those 14 H pluses to balance on the other side, I'm going to have to add some waters. Well, that's the only place the hydrogens could appear over here, so 14 of them would be enough for 7 water molecules. Well, and not by magic, but by design, the oxygens balance. Notice there were 7 oxygens on this side, and those 7 waters provided a place for those 7 oxygens to go. So, the extra step, again, is just a little arithmetic. You just got to look at the net amount of charge, ionic charge on both sides of the arrow. If it's in an acidic solution, add some hydrogens on there to balance that out. Add some waters, very likely on the other side of the arrow, to balance out the hydrogens you just added. Now, you'll find that this is a much easier method than separating the 2 half reactions from one another and then adding them back together. So, let's try a couple of them in basic solution. Okay, here we go. Here's one in basic solution. Now remember, when we run one in base, that means that when we go to balance the ionic charge, we're going to add hydroxides as our currency. So we get to add negative charges to whichever side of the arrow will balance out the charge, and then we can add waters again. All right, well, in this case, I'm going to go ahead and erase this part in base. We've established that. Let's go ahead and assign oxidation numbers. Here's our old friend, the permanganate ion. Turns out the manganese there is in its +7 state. Again, because the oxygens are -2 each. The iodide clearly is in its -1 state. The manganese in MnO2 is in a +4 state because the oxygens are -2 each. And if the oxygens are -2 each here, that iodine is in its +5 state. And we don't have to do any pre-balancing because we have 1 manganese on both sides, 1 iodine on both sides. So it's already a level playing field. Well, let's find out how many electrons were lost or gained. Well, apparently the manganese is our reduction. It went from a +7 state down to a +4, so that's a gain of 3 electrons. The iodide went from -1 to +5. That means it actually lost 6 electrons. So there's our oxidation. Loss of 6. Well, it looks as if we're going to have to double our reduction half reaction then in order to balance this out. So again, not too tricky on the arithmetic. Let's go ahead and double it. That means doubling the MnO2 and doubling the MnO4. All right, the hard work's over. Let's go ahead and erase everything here so we can kind of at least focus on the ionic charge. I'm going to go ahead and get rid of my arrows. We took care of all of this. I'm going to get rid of my oxidation numbers just so that I can focus on the ionic charges that are here on each of the species. Notice that the MnO2 was a neutral compound. It didn't have a charge on it when we started. All right, so that means there's 2 permanganate ions. That's 2 negative charges here. And the iodide was just 1 of them, so I've only got 3 negatives on this side. On this side, I only have 1 negative, just the iodate ion. Well, it appears since my currency of charge is hydroxide and it's negative, If I added 2 of them to this side, suddenly there'd be 3 negatives on both sides and it would be equal. Clearly I don't need to add more negatives to this side. All right, so if I add 2 hydroxides, suddenly I've got 3 negatives on the right side of the arrow. All right, well, let's add a couple hydroxides then over here. I'm going to go ahead and just put them underneath. All right, so now the electron exchange is balanced. The charges are balanced. I just need to tie up whatever loose ends. And it appears that I'm going to need a water molecule somewhere here. Oh, I'm sorry. I needed 2 hydroxides, didn't I? I thought, well, that's not going to work out. I said 2, and then I only wrote 1. Okay, so 2 hydroxides on that side. The charges are all balanced. Now, at that point, I've got 2 hydrogens on that side, none on this side, meaning 1 water molecule might do the trick. So let me put a water molecule over here and see if the oxygen's balanced. And again, they likely do. We've got 8 oxygens here. 1 more here makes 9. All right, well, it looks as if I've got 4 right there. 3 more is 7, and those 2 are 9. So sure enough, once you balance the charge, tie up that loose end, generally the oxygens at that point are going to balance. Otherwise, if something went wrong at the very last step, remember my advice. Go back to step 1 because you misassigned an oxidation number there somewhere at the beginning. Okay, well, let's try one more in base. And I think you'll see that this really is like the homework problems at the end of the chapter in our TRO text, that he likes these acidic basic. He doesn't do a lot of the molecular equations where you can't add anything. So if you use this as kind of a guide for doing the homework, I think you'll find it a little bit easier. Let me do one more example in a base. Okay, last example in a basic solution. So again, later we're going to have to add hydroxides and likely some waters. Now, in this case, we're starting off with zinc metal in its 0 oxidation state. It's reacting with a nitrate anion. Nitrogen here is in its +5 state. It's going to react to make ammonia. If you remember, ammonia is that weird one that has nitrogen in its -3 state because the hydrogens are +1 each. And a zinc complex with 4 hydroxides. Now remember, hydroxide has a -1 charge on it, and there's 4 of them. So that would mean this was a zinc +2 for that to come out to be a -2 ion. So that means the zinc is our oxidation. It went from 0 to +2. Loss of 2 electrons. On the other hand, the nitrogen went from +5 all the way down to -3. That's an actual gain of 8 electrons. Again, it went from +5 down through 0 and then all the way to -3. So that means in order to make the electron exchange balance, we need to fourple our oxidation half reaction. So let me take this times 4, which means a 4 in front of the zinc complex and a 4 in front of the zincs. All right, so hard part's done. We've got the electron exchange balanced. I'm going to go ahead and erase the arrows again, just to neaten things up. And we'll take away our oxidation numbers there. I left the ionic charges. Remember, the ammonia was neutral, the zinc was neutral, but the nitrate has a -1 charge, and the complex has a -2 charge, and there's 4 of them. So that means on this side of the arrow, there's actually 8 negative charges, 4 times that -2, but there's only 1 negative charge on this side. Well, I'm adding hydroxides that are negative, so clearly to balance this out, I need to add several to this side. As a matter of fact, 7 hydroxides would give me then 8 negative charges. All right, well, let me go ahead and add 7 hydroxides to this side. Now, the number of charges on both sides is equal. 8 negatives, 8 negatives. But again, the hydrogens and oxygens don't balance, so we're going to have to add some waters. But in this case, this is kind of odd. We're going to end up adding the waters to this side, the same side we added the hydroxide to. Well, that's because there's already a lot of hydrogens over here. I think there's 19. If we add them up, there's 16 right here, 17, 18, 19. So 7 of them are accounted for here, 7 hydrogens of those 19. So that leaves me with 12 hydrogens unaccounted for. Well, that means 6 waters. So I'm going to add 6 waters on this side. Now, suddenly, I've got my 19 hydrogens that appeared on that side of the arrow. Did the oxygens work out? Well, I've got 16 oxygens over here. 4 there and 4 times that. 16, well, it appears I've got 7 of them here, 6 of them here. That's 13. Oh, there we go. 14, 15, 16 in the nitrate. They balance. All right, so we did the trick. We got the electron exchange balanced. We got the charges balanced by adding the hydroxides. Balanced the remaining mass. All right, now balance in redox equations, again, like I said, kind of sets the stage for our discussion of batteries and electrochemistry. We see that there's an exchange of electrons going on here. And what we needed to look at then is how can we segregate these two reactions, get them in two separate beakers so that we can make those electrons pass through an external circuit and harness them to do some work. That's where the half reaction method does kind of come in handy, because it does show you how you could physically segregate the two half reactions and put them in two separate beakers. But personally, just to balance the equation, I find this a much preferable method. All right, so let's get on with the lab. I'll kind of walk you through what we would have done had we been in the actual lab. And again, the only thing that you have to turn in today is the pre-lab sheet with the redox titration lab. And it's just the 6 redox equations that I gave you some tips on earlier in our video. All right, well, let me get my lab report sheet and we'll get right to it.